everybody. Dave here today to talk about an outdated technology in the form of cathode ray tubes. These were all the rage back in the day when we had our big TVs and our big computer screens, but now it's more so a great physics demonstration instead. And so if you take a look at the diagram here, we have some key components that are clearly labeled. At the very left-hand side, there's a cathode, and attached to it is a heater. The idea of the heater is it's actually going to cause electrons to release from the cathode, from which we're going to draw them out and accelerate them towards the screen using some accelerating plates. From there, it's going to go through a processing couple of sections where we're going to change the intensity and we're going to change the focus using an electrostatic lens before it hits the deflecting plates themselves. The deflecting plates will cause the beam to bend predictably to any position that we want, and once they leave the deflecting plates, they go and they hit the fluorescent screen. Now, this is a basic model of a cathode ray tube. The actual cathode ray tubes involve magnetism as well, but for the sake of our discussion of electrostatics, we're going to stick with this to start. So the classic problem involves a two-step process. We have the idea that electrons are getting accelerated through accelerating plates, and then those same electrons are going to hit the deflecting plates, and deflection is going to take place. So the wording for a problem like this might start off as such. We have an electron beam, and we're going to accelerate it through a potential difference, and then we want to find the speed of the electrons on the other end. Well, as soon as we see the word speed, we know that we're dealing with the conservation of energy. So if I write this out here, we can see that we're stating that we're going to gain kinetic energy because potential energy is going to be transformed into this kinetic energy. If we take our delta EK and we break it down, EK final minus EK initial, we know that there is no initial kinetic energy because we're essentially stating that the electrons are stationary, which means that on the left side of the equation, we simply have EK final. On the other side, we know that there's another equation that can represent our change in potential energy in terms of the charge and the potential difference. And so based upon this equation, we can now plug in our values of charge of an electron and the potential difference that is listed to give us a final kinetic energy of 6.08 times 10 to the minus 17 joules. Now, if all we were going to do was calculate the change in potential energy, we would have the exact same magnitude, but we would have a negative sign in front because, again, we are releasing this energy. This is a key component of the conservation of energy. Well, now that we have this, there's only one equation that we know for kinetic energy, and that's 1/2 mv squared. And we're going to change this and solve for v. And so v is equal to the square root of 2ek over m. We're going to plug in our values. So EK is what we already calculated, 6.08 times 10 to the minus 17. And the mass is the mass of an electron, which is 9.11 times 10 to the minus 31 kilograms. And that's going to give us a value of 1.16 times 10 to the 7 meters per second. Something important at this stage of the game is to make sure that you don't carry every decimal place, but you carry enough, because as you'll find out down the road, we're going to have some different components of velocity that we're going to have to add to this, and the precision of the answer is going to be a very important point. So from there, what we do is we actually run these particles through the deflecting plates. So if I draw the deflecting plates again so that you can see them, we were given a couple of quantities. We were told that this was 9 volts up top and 0 volts on the bottom. We were told that the distance between the plates is 0.020 meters. And we were told that the length of the plates is 0.12 meters, like so. Now, this is an important thing to recognize. You'll notice that there's two distances listed, but when it comes to the calculation of various physical quantities, only one of these may be necessary. For example, the next step here is to calculate the electrostatic force. Well, we know that the electrostatic force is actually equal to QE. Well, E is the electric field strength, and to calculate that, we have to recognize that this is a uniform field situation, and we know an equation that gives us that as delta V over D. Now that distance is not the length of the plates, it's actually the distance between the plates. So if we plug in our values for our potential difference of 9 volts and our distance between the plates of 0.020 meters, we get an electric field strength of 450 newtons per coulomb. That will be the field strength that we use when we go to calculate the electrostatic force. We know that the charge of an electron is 1.6 times 10 to the minus 19. We know the field strength is 450 newtons per coulomb, and this is going to give us an electrostatic force of 7.2 times 10 to the minus 17 newtons. Now, something important about this calculation, you'll notice that I didn't use the polarity of the electron in the calculation of the electrostatic force. I'm only going to use polarity for scalar quantities because it will help me understand whether we are gaining or losing that particular type of energy. That being said, even in those cases, it doesn't bother me at all if you choose to understand the actual nature of that transformation at the end of the calculation. When it comes to dynamics quantities, though, I want to let my vector diagrams and understanding of dynamic situations to guide me in understanding the direction. So in this case, I understand that my electrostatic force is going to be 7.2 times 10 to the minus 17 newtons in magnitude, but the direction is going to come from my understanding of the electric field itself. If I draw the electric field, you can see that I'm going from high potential to low potential, but I have an electron coming in this way. Well, the electrostatic force, when applied to this electron, is going to cause a motion upwards, because remember, the electric field lines are the direction that a positive charge would travel. So again, I understand that in this case, this is going to be in a direction up. From there, we can calculate the acceleration because we understand from previous studies that for an object to accelerate, a net force must be present. And in this case, there's only one force present, and that's the electrostatic force. Now, some of you may be saying, well, hold on, these particles have mass, so there should be a gravitational force associated. And you're not wrong with that. However, the magnitude difference between them are so significant that we can actually consider the gravitational force negligible. Gravitational forces are actually much smaller than the electrostatic force. So based on this equality, we can solve for A as Fe over m, and we can plug in our values as we've already calculated, 7.2 times 10 to the minus 17, divided by the mass of an electron, which is 9.11, times 10 to the minus 31 kilograms, to give us an answer of 7.9 times 10 to the 13 meters per second squared. Now that may seem like an outlandishly large value. However, you also have to understand that when we're going between these parallel plates, it is an exceptionally high speed and they are not that long, which means this acceleration is not going to take place for very long. So don't worry about breaking the laws of physics and exceeding the speed of light, because that's just not going to happen here. This last question is certainly the most challenging because there's some previous understanding that we have to have. If we're trying to find the final velocity when the electrons leave the parallel plates, it's important to understand the path of motion that they take. So if I draw the parallel plates again, you'll notice that this uniform field is very much like the current gravitational field that we are all feeling in the rooms that we're sitting in right now. And so no matter where I go in this room, if I go to the ceiling or I go to the floor, there isn't so much of a difference that there's actually a noticeable effect on the gravitational field strength, meaning we are sitting in a uniform field. Well, if I took a massive object and I threw it through this uniform field, it's going to fly, as a projectile will, a parabolic path. Well, that's exactly what an electron is going to do when it flies through this uniform electric field. Is it will start off as a horizontal projectile and it will proceed to deflect until it leaves that particular field. From there, it will have some final velocity, which will actually be the vector sum of the velocity in the x direction and the velocity in the y that was just created. So this is a friendly reminder about two-dimensional kinematics. And so when I teach this topic, the thing I like to do is start off by listing all of the quantities I have in the x direction and in the y direction. And so the first thing I notice is that in the horizontal, there is no acceleration. The only force that's being applied is this electrostatic force, and it's pointing straight down. The only field in existence is straight down, which means in the x direction, we're dealing with a constant velocity scenario, which means I need my velocity in the x, my displacement in the x, and my time of flight. Well, my velocity in the x is the velocity that we already have, which in this case was 1.16 times 10 to the 7. Our distance in the x is actually the length of the plates, which in our case is 0.12 meters. The time, though, is something that I don't yet know. But I do know that the flight time is a scalar quantity, and it transcends this independence of vectors, meaning that the flight time in the x direction is equivalent to the flight time in the y direction. So now if I look at the y direction, I can find Vy initial, Vy final, acceleration in the y, displacement in the y, and the time of flight. So again, these two quantities are equivalent to each other. So I know I can calculate the time in the x direction, and then I can use it in the y direction. But what about my other quantities? Well, I know that there is no vertical motion initially, which means my vertical velocity is initially 0. I don't know what my final velocity is in the vertical. I do know that my acceleration, though, is going to be 7.9 times 10 to the 13 meters per second squared. That was the quantity I just calculated. I don't know what my displacement in the y is, and you're only going to need this if the question specifically asks for it. But again, if they ask for it, guess what? It is the exact same process. We still need to find the flight time, and then we can exploit kinematics to get us there. So the first thing I want to do is calculate the flight time. Well, I'm going to use my x direction, so Vx is equal to dx over t, which I can rewrite as time is equal to dx over Vx. Well, I can plug in my values of 0.12 over my velocity in the x of 1.16 times 10 to the 7, and I'm going to get a flight time of 1.034 times 10 to the minus 8 seconds. Here is where precision is going to be very important. Now, I'm going to do some funny rounding, and you may end up with different answers than I do. I strongly recommend that you carry your decimals all the way to the end and then round there, because two things are going to happen. Number one, we're dealing with very short times and very high speeds. And number two, when we calculate the velocity in the y direction, it's going to be a couple orders of magnitude lower than the velocity in the x, which means that the precision of those values is absolutely essential. So we never want to show 10 decimal places of precision in any calculations in anything we do in physics, but in this particular question, you're definitely going to want to show more than a couple of decimal places to show that the initial velocity, which is all horizontal, is not equivalent to the final velocity, which is now going to be on an angle. So now that we've finished our horizontal motion, we're going to go ahead and deal with our y direction motion. And we see that I now have time, I now have acceleration, and I now have my initial velocity in the y. There is a straightforward equation I can use to get my final velocity in the y, and that's Vf is equal to Vi plus At. We know that these are in the y direction, and we know that the initial velocity in the y is equal to 0, which means my final velocity in the y is simply equal to our acceleration, which is 7.9 times 10 to the 13 meters per second squared, times the time that I just calculated, which is 1.034 times 10 to the minus 8. And this gives us an answer of 8.169 times 10 to the 5 meters per second. You'll notice that the order of magnitude here is quite a bit different from the horizontal velocity, and this is going to matter when we combine the two. Now, we have our x direction velocity, we have our y direction velocity. Our total velocity now is going to be the vector sum of our velocity in the x and our velocity final in the y. And the direction is going to be the angle between them. So because I have two of the three legs of this right triangle, I can actually use the Pythagorean theorem to get my final velocity. So if I write this out quickly, I can see that Vt is equal to the square root of Vx squared plus V final in the y squared. And that gives us an answer of 1.1628 times 10 to the 7 meters per second. Now that seems pretty funny, and honestly if my students wrote down an answer like this for any other type of question, I probably wouldn't be very happy. But in this case, there's an important element that we have to consider. The y component was 2 orders of magnitude smaller than the x component, which means we have to show the precision to show that indeed that initial horizontal velocity is actually lower than what this velocity is. So it seems funny, but trust me, you have to show this. When it comes to the direction, we can simply use tangent of theta is equal to V final in the y divided by Vx. And if we use 10 to the minus 1 of this, then we should get an answer of around 4 degrees. So this is an important thing as well, because remember that they asked for velocity, not speed. If it's a written response problem or even a multiple choice, just watch the language carefully. Because if it says speed, then you don't have to do this calculation. But in this case, because it said velocity, we have to include both. So if we want to write out our answer now, all we have to do is say that it is therefore 1.1628 times 10 to the 7 meters per second at 4.0 degrees above horizontal. Just like you did when you were dealing with projectile motion. So this is an important element here. If you want to calculate the deflection, again, I'll extend my horizontal central axis, and you can see that this little distance here would be the deflection. The common misconception is to believe that the width of the plates, half of that is going to be the deflection, but there's no guarantee that the question is going to deflect it to the point where it just passes the end of the plate. So be very careful, my friends. You may run into some questions that get a little tricky. There is a conceptual question that comes up quite often with cathode ray tubes, and it comes down to what can you control to define the bend of the beam. And there are essentially 2 ways to make it bend more and 2 ways to make it bend less. And it comes back to the original question that involves these 2 mechanics associated with the accelerating plates and the deflecting plates. The first and most obvious way of increasing the deflection is to increase the deflecting voltage, because if you do so, you increase the electric field strength and therefore the electrons will deflect more. But the other one that isn't maybe as obvious is that we could actually decrease the accelerating voltage. Because if we decrease the accelerating voltage, what's going to happen is the particle is going to spend longer in the electric field, which is going to result in it deflecting more. So remember that the accelerating voltage is going to cause it to have a speed, and if we decrease the accelerating voltage, it will have a lower speed, so it will take more time to get through the plates. If we want it to bend less, then the inverse is going to be true. We can decrease the deflecting voltage so that the electric field is not as strong, which will cause a smaller deflection, or we can increase the accelerating voltage so that we end up with a higher speed of the electrons leaving the accelerating plates, so that when they get between the deflecting plates, they're going to be going faster so that they don't spend as much time in between those plates, thereby not deflecting much. So these 2 questions are absolutely essential in your understanding of the mechanics of the cathode ray tube. But with that, my friends, we have wrapped up our discussion of the cathode ray tube. There is a harder problem that involves now finding the deflection on the fluorescent screen itself, but I am sure that if you can get to the point where you know the final velocity coming out of the plates and you understand the mechanics that have caused this motion, then I have no doubt that the simple geometric type problem that involves your deflection on the screen itself should be easy to tackle. So happy problem solving, my friends, and we will see you again.